Okay, recorded. So, okay, for this 1 hour, we are going to touch a bit more, we are going to expand a bit more on what we have learned previously. A very quick recap. Previously, you learned how to do double integration, triple integration, and for the case of double integral, you have something from, okay, you have something like integrating over a general region. Remember, you must draw the graph and then you find the x is from this value to this value, and the y value is from here to here, and so on. And then after that, you choose your dy, dx, and so on. So that is an important part of double integral, because sometimes they don't nicely tell you what are the limits. What they tell you is simply the region is simply bounded by this function and this function. So we are going to expand on that part, where today we are going to look at parts where we will be using polar coordinates. So let me share you my screen right now. Okay, so I believe you can see my screen and my whiteboard right here. Okay, can anyone just clarify for me? Can you see the whiteboard here? I'm looking at the chat box. Anyone, if you can see the whiteboard, please say yes. Okay, nice. So now I'm confident everyone can see it. So, okay, double integrals in polar coordinates. I believe, I'm not sure whether in some previous subject you already learned how to read or write polar coordinates. So I'm just going to recap it again, just in case if this is something completely new for you. Okay, let's look at, polar coordinates. Now, usually, whatever that we deal with, x, y, x-axis, y-axis, all that is called Cartesian coordinates. Okay, so all that is Cartesian coordinate. Cartesian coordinate simply means x and y. Right? Why can't I? Okay. So Cartesian coordinate, oh my goodness, why can I write on it? One more attempt. Yes, okay. Cartesian coordinate is x and y, but there is another way of reading coordinates, which is called polar coordinates. Polar coordinates, we don't use x and y, we use r and theta. So all your coordinates are coordinates of r and theta, compared to Cartesian, which is x and y. This makes sense because, for example, look at this point right here. I would say that the coordinate of this point is, let's say x is equal to 2 here, just saying, and y is equal to 3, for example. Then the point here is the point 2, 3. Makes sense, right? Because the x is 2, y is 3. But in polar coordinates, instead of looking at the x value and y value, we are looking at this length over here. This length is what we call as a radius. And also, we are looking what is the angle of that line here going to that point. What is the angle from what do you call this? This axis here, from this axis towards the line, what is the angle? That is your theta. So you can also describe the same point by using another method, that is by specifying what is the length of the radius and what is the angle for the line towards the point. So let's do one example here. This is just theoretical, but let's do one example. Now from the triangle here, I'm not going to discuss in detail, but from the triangle here, by using Pythagoras theorem, by using sine, cos, tangent, trigonometry, I will be able to derive these four formulas, so-called formulas, right? So it's just from the triangle up there. I just derive it by using hypotenuse, adjacent, opposite, and so on. Now, if you know your x and y, and from there you want to get your r and theta, you can use the first pair of formulas here. On the other hand, if you know your r and theta and you want to convert it to x and y back, then you can use the second pair of coordinates here. Okay, but just keep in mind that in whatever case you're dealing with, you have four formulas to help you out. All four formulas here are formulas relating x, y to r theta. So depending on some cases, you might want to use one, some cases you might want to use two, some cases you might want to use both. So I can't really say unless we have a particular question. So let's do one example here, a simple one. This is a Cartesian coordinate. Square root 3, 1. Obviously on the graph paper you can plot. Square root 3 is a bunch of decimal places, not sure how much is it. But square root 3, 1 can be plotted in a graph paper. Now, if I ask you, convert this into polar coordinates. So, I know my x, I know my y. From here, I want to get my r and theta. So clearly, I'm going to use the first pair of formulas here. So my r here is simply square root of x squared plus y squared. So square root of my x is square root 3 square. My y is 1. So square root of square 3 plus 1, 4. Square root of 4 is 2. My theta, on the other hand, is, according to the formula here, the inverse tangent of y over x. So y is 1 over x is square root 3. I did this before the class just now. I got the answer was 30 degrees. Okay, just use your calculator. You will get 30 degrees. 30 degrees, or do you still remember how to convert from degrees to radian? If you want to convert 30 degrees into radian, you simply multiply the 30 by pi and divide the whole thing with 180. That's how you convert to radian. Because when it comes to integral, the limits, right? Usually we put radian, we don't put degrees on it. So in this case, just simplifying this would give me pi over 6. Okay. Alright. So this means my polar coordinates r theta is simply, my r is 2, my theta is pi over 6. So this is what I get from Cartesian to polar. But to convince you that this is true, yes, apparently Galal did it as well, 2 and 30. Just to convince you that this is correct, let me show you my favorite graphing application again, Desmos. What was the coordinate again? Square root 3 and 1. So we have square root 3 and 1. So this is the point here on the Cartesian coordinate, and there's an option to actually change to polar here, this. Okay, so that is polar coordinate. Yes, so can you see, when you change to polar coordinate, it is lying on the radius 2. This is the radius 2. And the angle, can you see the angle here is pi over 6, right? Zoom in a bit. So it's pi over 6 here. So it's lying on radius 2 at angle pi over 6. So what we did is correct. And you can always use Desmos to clarify it because it's so easy. You can always convert from polar coordinates back to Cartesian coordinate just to check if you're doing it correctly or not. Okay, so that is polar coordinate. Okay. Getting back to this, the whole point of this topic is not to teach you how to find polar coordinates. It was actually how to do double integration with polar coordinates. But I thought it makes sense to introduce first polar coordinates. So now at least you have a rough idea. So you can imagine we are going to use polar coordinates when you are integrating. Okay, I told you right before this, when you are integrating, the general region can be any shape. It can be a triangle, it can be a weird shape, it can also be a circle. So whenever you're dealing with regions that are kind of circle, Wenlong, did you accidentally click something because right, I received some kind of thing up there now. Anyways, so now, because whenever you are dealing with regions that are circular, right, those circular regions make sense to be described as r and theta, might make the work a bit easier. Okay, let us jump into a real example here. Okay, so now, this is the question, all right? This is the question. I just took it online because I feel it makes a good example. The integral itself is not tough. 2xy, a very simple expression. However, the region D down here, they did not nicely tell you x is from what to what, y is from what to what. Instead, they say that D is the portion of the region between two circles. One circle of radius 2, so I actually draw it here. One circle of radius 2 and another circle of radius 5. Centered at the origin, alright? So I draw it correctly here. That lies in the first quadrant. So is the portion between the circles lying in the first quadrant. If I want to shade it, it's going to be something like this. So this is the region they are talking about. First quadrant. Quadrant means the separation of your Cartesian coordinate. This is the first quadrant, second quadrant, third quadrant, fourth quadrant. Okay. So this region, let's say if you don't even know anything about polar coordinates, I just ask you to solve this. So one way that I would do it, okay, keep in mind this is without using polar coordinates. I want to compare both. Without using polar coordinates, do you still remember what is the equation of a circle with the origin being 0, 0? Do you remember what is the equation of a circle? It is simply x squared plus y squared is equal to r squared. This is the equation of a circle. So for the inner circle here, all right, for the inner circle, the equation is going to be x squared plus y squared is equal to, the radius is 2, so 2 square is 4. That is the equation, right? Or I can also rewrite it by making y as the subject, just purposely. I can rewrite by making y as the subject. It's going to be square root of 4 minus x squared. Okay. As for the outer circle, right, the outer circle is going to be x square plus y square is equal to r square. The r here is 5, the radius is 5, so r square is 25. Or again, I can purposely rewrite it if I want to. Y is equal to square root 25 minus x square. Okay, so this is how I would do by using x and y if I don't even know that polar coordinates exist. But let's look, what is the problem when you do it this way? The problem is that now if I look at the limits, x is from 0 to 5, okay, that's not so problematic, that is just fine. X is from 0 to 5, but y, can you look at y? Y here is always from the inner circle to the upper circle, inner circle to the upper circle, inner circle to the upper circle until 2. After 2, it's 0 to upper circle, 0 to upper circle. So can you see there are two regions here? Before 2 is from the inner circle to the outer circle, but after 2 is from 0 to upper circle. Meaning that if you actually want to write the limits of y, it's going to be the inner circle, which is 4 minus x squared, to the outer circle, which is 25 minus x squared. This is only true when x is from 0 until 2. This is only true for x until 0 to 2. But when x is more than 2, when it is from 2 to 5, all right, now it becomes y from 0 until the outer circle. So not to say this is impossible, it is still doable. What you have to do is that you have to break down the integral into two parts. Okay, you have to break down the integral into two parts. Because of this, right, you have to break down the first integral by using these limits for x and y, plus the second integral by using these limits for your x and y. So it's more work because you have to compute two different integrals and finally add the answers together. Not impossible, but a bit hard. But now that we have the knowledge of r and theta polar coordinates, there's an alternative way to do this. So let us do the alternative way. Again, the same circle. Why not, instead of reading it as x and y, I try to read it as r and theta. Okay, if I look, again, let me just shade the region so that we are clear. We are still talking about the same region. Okay, now instead of looking in x direction or y direction, I'm looking in terms of radius. Can you see that no matter where I draw, see, no matter where I draw it, the radius is always from the inner circle to the outer circle. No matter where I draw my line, the radius is always the same. So my radius is from the radius of the inner circle, which is 2, to the radius of the outer circle, which is 5. So that's done. How about my theta? Alright, we read our theta from the x-axis in the is it clockwise or counterclockwise? Counterclockwise direction. That's how we read it. Okay, it's a normal standard way of reading angle. So my angle starts from 0 exactly here until it goes and stop here. It's a full 90 degrees. So it's from 0 until 90 degrees. But again, in integrals, we rarely use degrees, we use radian. So 90 degrees is actually pi over 2. And there you have it. The limits are way easier compared to the limits up here. This limit is way easier when you look at it in terms of r and theta. But of course, now there's another problem. The original question was integrate 2xy dA. But now we have described everything in terms of r and theta. So you have to convert the whole thing into r and theta. But luckily, do you still remember we have this formula here? X is equal to r cos theta, y is equal to r sin theta. So because of that, it doesn't become too complicated. Let me just try to write it. So my 2 is 2. My x is r cos theta. My y is r sin theta. Okay, dA, usually we would write it as either dx dy or dy dx, depending on the situation, isn't it? But now, we are going to write it as dr theta or d theta dr, because these are the two variables we are using. And another important point here, please keep this in mind, very important. When you use polar coordinates, you have to multiply r. So not only do you have to write dr theta or d theta dr, you have to include r. That's the way the conversion works. There's a whole mathematical explanation behind it, but I'm not going to go into geometry here. Just remember that when you introduce it polar coordinates, you have to put in r there. So now I don't see any problem. I can choose dr theta or d theta dr. So just out of preference, right? Let me choose dr d theta. And of course, I must put an r here. So since I integrate with respect to r first, the r limit should be the inner limits. The outer limits is for theta, which is 0 and pi over 2. So this is the integral you have to work on now. Okay? And since we have time and we are doing this, let me just show you the complete steps, how I would do this. Maybe you will do it differently, not sure. But first thing first, let me just simplify everything because I see it's a bit complicated here with a lot of cos, sine, a bunch of r. So the 2 remains 2. There's an r here, there's an r here, there's an r here. Altogether, they are r cubed. Cos theta and sine theta, I can't do much. Let me just write it here. And then a dr d theta. Okay, so now I'm integrating with respect to r first. Remember the inner integral first, then only the outer integral. So 0 to pi over 2. If I integrate this with respect to r to the power of 4 divided by 4, so it becomes r square over 2. R4 over 2. And cos theta sine theta with a d theta out here, and the limits are 2 and 5. Okay. So yes, I did this question just now before the class to make sure I don't do it wrongly. And when I substitute in 5 and 2, you can try it out. What I got was, okay, let me just write. Oops. Okay, so what I got after I substituted it was 609 over 2, and then a cos theta sine theta. This is what I got. Okay, d theta. Now, this integral a bit tricky because I have cos and sine at the same time, but if you do enough practices, you will see that this can be done by using substitution. Why not I let my u to be sine, because I know if I differentiate sine, I will get cos. So therefore, du over d theta is differentiate sine, you get cos, and therefore du is equal to cos theta d theta. This is not something new, just a quick recap of how to use substitution. And because now we are changing everything to u, we have to change the limits as well, right? Don't keep the limits because now we are changing everything. So when theta is equal to 0, right, your u becomes sine 0. Sine 0 is 0. When your theta is equal to pi over 2, your u becomes sine pi over 2. Pi over 2 is 90, sine 90 is 1. So u is equal to 1. So these are your new limits. So now by using this substitution, let's transform everything here. So my limit is from 0 until 1. 609 remains 609 over 2. Okay, the sine theta part becomes u. The cos theta d theta part becomes du. So there you have it, a way more simpler integral. If you solve this, right, it's going to be 609 over 2 u square over 2. I just integrate the u, put in 0 and 1. What did I get? I get a 609 over 4. So this is what I got. Okay, so this is not a new thing here. The new thing is actually polar coordinates. What I wanted to do today is to convince you that in some cases, rather than doing it in terms of x and y, if you see that they are in the form of circle, it makes sense to describe by using theta and r, go for it. Okay, but usually in your quiz or test or exam, no worries. If you are required to change into polar coordinates, I will mention. So you don't have to cram your head like, should I change or should I not? I will tell you if you need to change, right? But what's important is that today you know how to describe a region by using polar coordinates. Okay? Alright, so I want to give you one exercise to try it out. But before that, do you have any questions on this? I don't expect you to be able to immediately memorize all this, of course, impossible, but at least you have a rough idea. So, do you guys have any question? Otherwise, I will proceed to give you an example. Okay, so I see that none of you have any questions. Alright, so let me stop sharing my screen for a while. Okay, and I will post you a link in the chat box right now. Of course, I will provide you the solution as well. Just try it out, scribble on a piece of paper. Okay, give me some time, let me check it out. Alright, so I found one question. Okay, I'm trying to screenshot the question and attaching it in the chat box here. It's going to be very small, so hopefully you can click on it and zoom in on it. Right, so try out this question right here. I believe in you, so you don't have to show me all your working or whatsoever. Just share with me the final answer that you get. Okay, and use polar coordinates to help you out. If you are stuck, you can always ask me question either in the chat here or a private chat, okay? Doesn't matter. Alright, so I've attached the formula here in the chat box for the conversions XY. As for Tanish, how to get theta using Desmos? Actually, to get the theta, you just have to plot the region and then see what is the angle of the region. I haven't tried out this question yet, but once you sketch, it's just from the sketch you need to figure out how much is your region from the x-axis and then how much does it rotate. Okay, give me a few seconds, Tanish. Let me try to draw the region and see how it goes. Yes, Tanish. Okay, when you're doing this question, they are, okay, let me look back at the question. It says that D is the region in the third quadrant between this function and that function. Actually, both of them are just equations of circle. So you have to draw the two circles first and then see the region enclosed by them in the third quadrant. So if you draw them correctly and look at the third quadrant, okay, let me see, full meaning, send something here. Yes, it's exactly the region sent by him here. It's actually a complete circle, but you're only looking at the third quadrant. So from here, you can actually guess what the angle is, right? The angle is from 180 degrees to 270 degrees. Or if you convert it to radian, that would be from pi to 3 over 2 pi. Yes, Dharmi. So you actually plotted the two circles, is it? I can see the two circles. And then, okay, one. Okay, so between the two circles, there's a whole donut-like shape, right, between them. But then you're only going to look at the third quadrant. Yes, it's actually -1 and -3. But then when we talk about the radius, what matters is actually just the length of the radius, isn't it? So the -1 and 3 in terms of x, correct, it should be -1 and 3. But when it comes to radius, it's just 1 and 3. As for the angle, it's between 180 degrees to 270 degrees. So you guys try it out now. I'm going to share with you the solution, the complete solution. If you're stuck, you can refer to it. Okay, so at this point, don't immediately refer to the solution. Try it out first. But of course, if you're stuck, at least you can refer to this. Let me send you a link containing the complete solution. So check it out if you are stuck or to make sure that you are in the correct path now. So remember that we only use Desmos to plot the functions and to see what the bounded region looks like. So once you have identified the bounded regions, just quickly sketch the bounded region on a piece of paper, and then from there identify what is your x, what is your y, and so on. Alright, I just realized that I've been talking without opening microphone just now. Anyways, so what I was saying is that I'm not sure whether some of you are still having problems to find the radius or the theta. But if any of you are still having problems to find the theta, then this is how it works. I simply plotted the two equations into Desmos, or by experience you actually know that the two equations are simply equations of circle, one with radius 3, another one with radius 1. So the bounded region is actually everything inside, I know, everything inside here. However, they only say that look in the third quadrant. So therefore I only look at this region. At this region, I see that the radius is from the radius of the inner circle, which is 1, until the radius of the outer circle, which is 3. Although the x value is negative 3, but since the radius, the length is still 3, we don't put negative there, right? As for the theta, there's no way to find it out unless you just analyze whatever that you draw. So I see that my circle, because we read it in an anti-clockwise direction, we don't read it from here to here, we read it the other way around. So from 180 degrees until 270 degrees. So another way of writing 180 degrees is pi radian, and 270 degrees is 3 over 2 pi. Okay, so just want to put this out so that everyone knows how to find the radius and theta. The integral, of course, you have to do it yourself now. Okay, right, going to stop sharing the screen again. And do let me know if you get the same final answer as the solution I showed just now. Meaning the previous solution, as in the one that I draw just now, or the complete solution? I did just send a link just now, right, in the chat box. If you actually click on it, it's the complete solution for the problem that I just gave. Or if you want to see the circle that I draw, I can show it to you again. I do realize that trigonometric integration is not really something that is fun, Because first of all, often you will have to use some kind of trigonometric identities, this and that. So what I will do is that after the class today, I will Google for all the basic trigonometric identities and I will post it in the group so you can have a look at it. If it is basic like 6 sine theta, 6 sine square theta, you don't need to use any identities. But in this case, I see that at one part in the solution, you have to use trigonometric identities. So it makes sense for me to actually provide it. Okay, so as for now, just bear with me and try to follow along the solution given. But in the future, especially after the class today, I will provide the necessary trigonometric identities. Alright, just realized that the time is about 12:09 already. Our class is going to end at 12:15. So just try it out, no rush, okay? Try it out. If you are stuck, let me know. As for the last few minutes now, let me open up the solution. No, let me open up the QR code so they can scan for your attendance, right? So everyone be alert. Let me share my screen now. Give me a second. All right, so here you go. We have 4 more not being able to put the attendance here. If you're having technical problems, just let me know after the class, right? I'll manually key you in. Okay, so I'm assuming 2 of you guys are having problems to put the attendance. It's okay. I'll check who it is later. Uh, Tanish, I'm not sure which previous solution do you mean? You mean the one that I draw? Alright, so it's okay, just get back to me after class. As for the others who have no questions for the moment, we are done for today, right? So just polar coordinates. The next time around, we will still be in chapter 1, but we are almost reaching the end of it. Okay? So as for now, we are done. So I see you guys again on, not sure what day, but for our coming class. The first one that I started. Alright, let me do this, Tanis. Let me share the whole whiteboard with you. Then maybe you can check out the part that you wanted. Alright? So I'll share with you the whiteboard in a while. I'll put it in the group. You can check it out. So as for the others, you are free to go. See you guys again then. Bye.
Thank you, sir.
Okay.
Thank you, sir.
Welcome.
See you.